continue from where we left. We were talking about modeling, right? A single degree of freedom system. And what that means is how we can identify a single spring or stiffness element and a single mass element, so we can find the natural frequency, which is K over M, or for that matter, solving the equation of motion. So as I said, we are going to spend some time focusing on that. And the first approach that we are using is for simple cases. Simple cases, meaning you're given a problem, you're given a structure that is easy to derive, easy to set up a free body diagram, dynamic free body diagram, or dynamic equilibrium free body diagram, and derive the equation of motion directly. There are many simple systems that you can find the equivalent system that way. So I'm going to do more problems. I believe 1 or 2 problems last time. Let's do 1 or 2 more this time. Let's say you have a very simple structure that basically consists of a rigid bar and a spring that is attached to it. This bar is connected to a pin so it can rotate. Due to some disturbance, can oscillate. So it goes through a rotational motion like this, back and forth. Let's say the mass of this bar is given. Mass is M. Length is given. And you want to find the equivalent mass, the equivalent stiffness, and let's say find the natural frequency. So this is one of those straightforward cases that you can apply this approach. So the step 1 is you just set up the free body diagram. So free body diagram means after this has gone through some deformation or motion, use the lumbar principle to set up the free body diagram. So if this thing moves in that direction, obviously this spring goes through some deformation, will experience deformation, and that deformation, due to that rotation, angular motion would be what? If this is L, this would be L sine theta, and if the angles are assumed to be small, this would be L theta. Then you have this mass acting through the center of mass, so that's another force, and this is moving in that direction, so you do have also an inertial force, rotational inertia, like this. And you have these 2 forces that are holding this, if this is A, AY, and AX, that are holding this bar in place. So this is the free body diagram, or using the lumbar principle. So you just write the equations of motion that way by summing the moments about point A, the point of rotation. So you have I theta double dot go in that direction, the moment of mg about point A would be this distance times that force. This distance is L over 2 sine theta, and again, if this is a small, would be L over 2 theta. So the moment that this generated about point A would be then plus mg L over 2 theta, okay? So that's that. What else? Then you have the moment of this force about that point, so you have plus Fk times this distance, which is L, okay? And of course, F itself would be the stiffness times the displacement that this experiences, which is L theta equal to 0. So let's simplify that or rearrange that, reorganize that. I, for a rigid bar rotating about at this point, if you figure that out, would be, what was that? ML squared over 3, okay? Theta double dot. Let's factor out whatever for the theta terms. You have plus mg L over 2 plus k L squared theta is equal to 0. So this is, once you set up the equation of motion, you compare that with the general form that we have for the vibration of a single degree of freedom system. So whatever is the coefficient of the acceleration term is your m equivalent, and whatever is the coefficient of the displacement term is the k equivalent. So that is your equivalent system. Or this is the single degree of freedom system, and natural frequency, which is k equivalent over m equivalent, then would be mgl over 2 plus k L squared divided by ml squared over 3. It can be simplified. This cancels out, so it would be mg over 2 plus k L over m L over 3. Of course, you can further simplify that, but that's good enough. So that's, yes?
Before you drew the switch on the K on the equation, is that a minus or plus?
This one?
Yeah.
Oh, this is the equation of motion.
Yeah.
Yeah, for a single degree of freedom system. Any question? Any other questions? Now, let's do another problem. Okay. Let's say you have a rigid bar, massless, rigid bar, with a tiny lumped mass at that end. It is supported at this point through this hinge, and then you have a spring support at this end. Length of this piece is, let's say, I have that A, length of this piece is B, okay? And this goes through some oscillation, like this. And we want to set up the equation of motion, and through direct derivation find the natural frequency or the equivalent system. So if this thing is oscillating, going through some small displacement, if this experiences a rotation theta, this is a rigid piece, so this mass would also experience same rotation. So this angle is also theta. So what would be the free body diagram then? This would be the free body diagram. The motion is in this way, so you have I theta double dot. I corresponds only to this mass because this is assumed to be massless. You have these two forces here. Force of the spring, okay? And then, of course, you have this mg. So that's the free body diagram. Okay? So if that's the free body diagram, you write, again, summation is a rotational motion. So with the rotational motion, you write summation of moments equal to 0 about this point A, right? So just take summation of moments here. So you have this force times this distance, which is A. So you have F going that direction. So Fk times A. Then you have mg times this distance going also, this goes in this direction, this goes in the opposite direction. So it would be mg times this distance. If this is b, this is theta, would be just b times theta. Or b times sine theta, which is, assuming a small angle, would be theta. Then you have the I theta double dot. And that's it, equal to 0. I, in this case, is, as I said, is just a moment of inertia of this lumped mass rotating about point A. This is a point mass, so it would be just mb squared. What is this force? This spring is experiencing this deformation, so the distance that it is going through would be just a theta. So this force would be k times a theta times a. So let's simplify this. You have mb squared theta double dot. So it's mb squared theta double dot. Let's factor out theta. You will have plus k a squared minus b m g, okay, times theta. So this is the equation of motion. Yes?
For the sum of moments, why did you say that the first one is Fk times A and not like A cosine theta?
Which one? This one?
Yeah. Wouldn't that be A cosine theta? Because
You-
A is
you-
the length of the ball.
Yes, it can be cosine, but again, when theta is very small, cosine theta is 1, right?
Yeah, okay.
Almost 0, so it would be 1. Good
Why don't
point.
we include theta then like we do the other parts?
Say, you mean this theta?
Yeah,
Yeah, would be, why is it the same?
yeah.
Because this is rigid. So if this piece rotates theta, that goes also theta, right? Like, I have shown that here. Any other questions? Yes.
How come you keep setting the sum of moments equal to 0 instead of just putting I theta double dot?
Right, if this is moving in this direction, this is the lumbar force. So when you put the lumbar force, that's the lumbar principle. If you put the inertial force on the diagram, instead of writing summation of moments is equal to what? Would be always summation of force is MA or I theta double dot, right? Instead of writing it this way, summation of moment, I've already taken it, consider that into the diagram. Summation of moments becomes 0. So the lumbar force, you put it in the opposite direction of motion, right? So the problem becomes like a static equilibrium. By including the lumbar force, you have the dynamic equilibrium, which is similar or analogous to static equilibrium. Sum of forces equal to 0, sum of the moments equal to 0.
then does it matter to you if we do it that way or if we just do
Doesn't
sum
matter,
moments equal activity?
they're identical.
Okay.
In fact, there's a problem, homework problem that asks you use both Newton's, I guess, approach or the lumber principle to prove that they are the same. Yeah. Yes.
When would you include the translation of the centered mass with the lumbar force as well?
You mean, when do you include this force?
Well, because you have it for the rotation.
Right.
Would you ever have the rotation and the translation of the centered mass?
Well, this is basically the rotational motion, right? So what you're saying that, okay, also this is also moving as this is moving in that direction. This is also moving, the mass is moving in this direction, right? That's what you're saying, right? We are ignoring that, basically. If there's, because at that distance is very, very small. Any other questions? Okay. So if you look at this then, just analogy or compare that with mu double dot plus ku is equal to 0. This term is this, the mass equivalent, and this term is this k equivalent. So the natural frequency, which is k over m, becomes k squared minus bmg divided by mb squared in this case. Okay, any other questions? So as you can see, for simple cases, and I emphasize simple cases, definition of simple case is that you can simply set up the free body diagram. You have a simple structure, you set up the free body diagram and directly derive the equation of motion, and you can set up basically the natural frequency, find the natural frequency, find the equivalent system. Before I basically introduce the other cases, or when the system is getting more complicated, I should emphasize on the fact that in doing the modeling, the piece that is most difficult or is most important to really understand and identify is the stiffness element. As I said, every structure is made of many pieces. You've already seen that in the statics. You may be dealing with a truss that is made of many basically axially loaded members, two force members, or a frame that is made of several pieces that each of them is a beam element, or can be a truss element. So when you have a complex case like that, each of those pieces have a stiffness, can be represented by a spring, based on the definition of the spring that I introduced. You remember we said that the stiffness, you remember the stiffness definition of a stiffness is a force that generates a unit displacement. So if for each of those elements, if we can find somehow the stiffness, how all of these add up when the structure goes through deformation. In other words, let's say you have a building, all these columns. So when the structure moves, how can you add up the effect of all the columns that represents the stiffness terms? If you have a rotating machinery, you have all these supports that represent bearings and whatnot, so you can replace them with some equivalent stiffness for each of them. How do you add up the effect of all of these? In order to do that, we basically look at two cases that are really the dominant or the most common case, at least when it comes to mechanical vibration. Of course, there are more complicated cases like that too, but there are two cases that if you really understand, we will be able to replace all the stiffness element in a system with a single stiffness element. And we're going to study that. These two cases are basically this. Either all the stiffnesses, and as you can see, I emphasize stiffnesses or stiffness element. Stiffness elements, we call them springs, because we are dealing with only a one directional motion. In other words, in vibration, we are assuming that each of those elements experiences just either an axial deformation or rotational deformation, but just one deformation or one degree of freedom. So if either all the stiffness elements experience the same force, we call this springs in series. The second case is all spring or the stiffness elements experience say deformation. Okay? We call that case parallel. If this is, the stiffnesses are parallel. Why do we use that terminology or even that analogy? In fact, as you can see, using basically the same similar approach that you probably remember from electrical circuits, combination of resistors, you can establish that analogy and find the equivalent stiffness, and then we will of course interpret that and really try to understand the physical meaning of it. So case one means this. Let's say you have, to start with, let's say you have two springs with different stiffnesses, but they are subjected to the same force. Okay. Obviously, each spring goes through different deformation. You have two bars, we've connected with each other, subjected to an axial load. Each bar, depending on its geometric and material properties, will deform differently or elongate differently than the other one. So let's say this one, if this end goes through a displacement U1 and U2, this bar will experience a displacement that is U1 minus U2. And if this end moves that amount, this spring would experience a displacement which is U3 minus 2. So what we want is, or the question that we're asking is it possible to replace both of these with a single spring, which I call that an equivalent spring, like that. Let's say, for instance, you have two shafts as part of a rotating system, like this. You don't like that. You have a non-prismatic structure. This is different in diameter than this one. So is it possible to replace both of them with a single shaft, which requires that we find the stiffness of this that would be equivalent to the combination of these two. Okay? That's what we're trying to do here. So let's look at basically these. So we will look at a free body diagram of each case. What we have here, in the first case, each of these are subjected to the same force. So the spring number 1, okay, will experience this deformation, U2 minus U1. So that's the relationship between the force in that spring and its stiffness and the deformation that it goes through. With the spring number 2, we have this relationship. It goes through this deformation, so that and this experience the same force. The spring that we want to find, which would be replacing the combination of these, or is equivalent to some of these stiffnesses, would be experiencing this deformation, U3 minus U1, right? Because that's what these two ends will experience. So from here, let's rewrite this like this. I write that F over K1 is equal to U2 minus U1. In this case, F over K2 would be U3 minus U2, and the stiffness that we want to find, if we can find that, would have this relationship with those displacements. But then we look here. If we add these two, okay, F over K1 plus F over K2 is what? U3 minus U1. So this is then equal to this, or F over K equivalent that we are trying to find would be F over K1 plus F over K2. F's are equal, so therefore we can reach the conclusion that if two springs are in parallel, we can replace those two with one single spring, and this is the stiffness of that spring that we need to find. Okay? And of course, if you have more than more than two springs, you can easily show that if you have n number of springs, in fact 1 over K equivalent is simply I is equal to go from 1 to n of 1 over K I. So for two springs, for instance, K equivalent then would be K1, K2 divided by K1 plus K2. Okay. So that's basically how you find that equivalent stiffness. The important, of course, thing here is, what do we mean by series? Because series does not necessarily mean that they're connected like this. Okay? For instance, if you look at, a good example can be, if you have these shafts, okay, connected together and experiencing a a vibration. Okay. Since these experience the same moment, or say torque or torsional deformation, they are said to be a series. But physically, as you will see, as I also introduced the concept of parallel, that series does not necessarily mean that they have to be physically connected like that. They can have different geometric configuration, but as long as they experience the same force. Okay? So one, as long as we have the geometric and material properties of each one, G2, J2, L2, you remember that we said that the stiffness for a shaft element, for a bar, you remember for a bar was what? And we use a direct definition of a stiffness. If the displacement is PL over AE, and the stiffness is defined as a force that generates a unit displacement, so K for a bar is AE over L, and for a shaft, KT is JG over L. So in order to replace these two with a single shaft, I can just write 1 over K torsional stiffness that we want to find would be 1 over G1, J1 over L1 plus 1 over G2, J2 over L2. Or you can simplify that as K 1 over KT would be L1 over G1 J1 plus L2 over G2 J2. Of course, you can further simplify that, but that's how you find a single shaft that can replace those two. Okay? So that's the definition of springs in series that you come across in many cases. But what does the parallel mean? Okay? Parallel means that the spring or the stiffnesses experience the same deformation. In other words, let's say you have these two springs like this, subjected to a force, but the stiffnesses are different, and you want to replace these two with a single spring. In this case, both of these experience the same deformation. So, from the free body diagram, you know that this is F. The only information you have is the total force. F would be sum of the forces that each spring due to each deformation experiences. So F1 is what? Is K1 times U2 minus U1. And F2 is K2 times U2 minus U1. So if you want to replace both of these, again, with a single equivalent spring, that spring would experience the same, would be subject to the same deformation. So that spring would be K equivalent times U2 minus U1. Force of that spring would be its equivalent stiffness times the same displacement. So as you can see, these from the two sides cancel out. So if the springs are in parallel, the total stiffness would be the summation of them. Okay? And of course, again, if you have a large number all in parallel, then in general, K equivalent would be simply I from 1 to N of Ki. In finding the equivalent stiffnesses, the most important part is not how to add them up algebraically using this equation. The challenge is to really figure out whether the springs are in parallel or in series, right? Let's say you have a beam like this, a cantilever beam, okay? And two springs like this are connected to the tip, and this is oscillating, right? You would say these two are in series, right? Because they're connected in series. But that's not true. Look at the whole system. If the system is going through some deformation, this beam would go through this deformation, delta, that those springs also experience that. So all these three pieces are actually in parallel. So it's not the geometric configuration, but it is the understanding of whether the mass is supported by whatever number of stiffnesses, and if those stiffnesses experience the same deformation or the same displacement. If they're experiencing the same displacement, so if this is K1, this is K2, and this is, of course, 3EI over L cubed, then the total stiffness would be K1 plus K2 plus 3EI over L cubed. So these can be bars. For instance, this can be a 2-force member like this, A, E1, L1. So this K1 would be A1, E1 over L1. That's all. Why is this so important? Think about, for instance, if you cannot detect the fact that you have a system with all these supports, but it happens that all these supports and their configuration is such that, in fact, they're in series, okay? So you want to find the equivalent stiffness, right? You would be using this relationship, right? If you do not realize that these are in series and you want to avoid the vibration, you say, I'm going to stiffen the system by stiffening, for instance, this piece. If they're in series, and these are quite weak, if you stiffen this, what happens? Let's say you increase this to whatever extent you can. This actually goes to 0. So in other words, by stiffening one component, if the elements are in series, you're actually weakening the system. Which sounds kind of odd, right? But if they're in parallel, obviously, as you add up the stiffnesses, the system becomes stiffer and stronger. So the important thing is that to differentiate, and from the physics of the system, by looking at it, by understanding how the deformation takes place, to figure out whether these are in series or in parallel. So let me do, since we have the time, let me do an example here, okay? Okay. Okay, I'll do a quick example, a simple example. In the other class, we just ended up to getting to this point. We didn't have much time left, but since we have here, I may as well do that. Let's say you have a beam. Okay. There's a mass here. Okay. And so you connect this to a bar, A over L, okay? And that same example that I gave you, so this system is vibrating, and we want to find the equation of motion, or find the equivalent stiffness and the equivalent mass of the system. Okay? So the first thing that you need to realize that as this is going through the deformation, what is happening here? As I said, if you look at the oscillation, if it's a small oscillation, as the beam goes through this displacement, delta, all three of them would experience the same deformation. So if I call this K1, K2, and K3, equivalent stiffness would be 3EI over L cubed plus A1 E1 over L1 plus A2 E2 over L2. So this is the stiffness of the system, and then you can simply write the natural frequency, which would be that K equivalent over the mass of the system. There's a good problem in your homework that is something like this. I don't remember exactly, but it is something like this, which is a very good example. This torsional system is going through some rotation. Radius of this disk is given as R, and this is going through some rotational motion theta. So as this disk rotates, right, what happens to these? These two, right, experience what? Same deformation or same displacement? They would be subject to the same force, right? So these two are in series, okay? How about these two then? These two, you have a shaft, okay, and this one. As this thing is rotating now, okay, what happens to these two?
Same definition.
And then, how about these two?
Same.
These two, as this thing is rotating, experience a displacement which would be r theta if the angle is small, right? So as you can see, although they're attached in some weird configuration, but nevertheless, they go through the same displacement. So you need to just add them up. So the replacement for these two would be a, so you basically would have a single spring as this is going through the deformation. This one, and this one would experience the same deformation. So it would be all in series, all in parallel. So that's a good example. You may want to meet as a team and think about it, but that's a very good example that it is not important to be able to apply these equations. The most important part is to figure out if those stiffness elements experience the same force or the same displacement. Yes?
How did you know that you did need an equivalent for the?
Oh, because you mean for that one or this one?
That one.
Oh, this is just a lump mass here, that's it.
Okay.
This one is massless. These are all.
Even though it's, because it's kind of rotating about so much further down.
Right, but these are massless. All these are massless. So you're assuming a small oscillation like this.
Okay.
So only this mass is going up and down. And the displacement would be also linear.
This example